All right, this video is going to hit some of the highlights of the Chapter 3 and 4.1 review packet that you got in class today with the substitute, if you're with Mr. Freeland. I originally recorded this video, but there was no sound, so this is the second recording of this. So I'm just going to go through some of the multiple choice pretty quickly if it's pretty straightforward. Number 1 was D, and all that required was us plugging in 95 into this regression equation. Number 2, we were asked to find the residual. Okay, we just need to remember that residual is the actual value minus the predicted. So we're given her actual value. We computed her predicted in the problem before, and we need to subtract those two, and we end up with positive 2.5. Number 3, all but one of the following statements contains a blunder. Which statement is okay? So each one has a problem except for B. B is okay. So let's go through the other ones to make sure we know what the problem is. A says there's a correlation between the position and weight. Position is categorical. Okay, correlation measures the strength and the direction of the linear relationship between two quantitative variables. So A is out. C, it gives us a correlation, but gives us a unit. Okay, correlation is unitless. We would never say that the correlation is 0.71 miles per gallon. So C is out. D is out because R is between -1 and 1, and in D, it's greater than 1. And then E is out because of the same reason A is out. We have two categorical variables. We can't measure the correlation between those two variables using this measurement. Okay, number 4, what is the square of the correlation? That's R squared, and that's called the coefficient of determination. Well, that measures what D says. Okay, and that's sort of our canned interpretation of the coefficient of determination. It's the fraction or the percentage of variability in the values of y that are explained by the model. Okay, number 5, which of the following statements are true? If you look at all these statements, they're all true. Okay, number 6, linear regression employs the method of least squares. You should understand what that means. Okay, and this question gets at that. You should be able to explain what that means. Hint, hint, for the test. So, when we run a regression, so we have some points, okay, and we fit a line to those points. The least squares line is the line that takes the y distances, which are the residuals, to the point in the line and squares those distances and minimizes the sum of those square distances. That's what least squares does. So we're making the area of these yellow squares as small as possible. The quantity that's minimized is the one that's listed in C. Okay? So it's the sum of the squared residuals. All right, so the answer is C for number 6. For number 7, you should recognize this as an exponential model. And to transform data that are exponential, we will take the y variable and change it into the log of the y variable. So that's why B is correct. For number 8, using that equation, we have to find the residual for t equals 6. So we're going to plug in 6 into this equation up here, get our actual value, and subtract that from, or get our predicted value and subtract that from the actual, and so we get negative 0.014. That's D. All right, moving on to the free response. We're talking about predicting the yield of the lumber that comes out of tree, and we measure that in board feet. And so you should be able to interpret Minitab output. You should be able to find an equation from output like this, and we can see that R squared is 0.953, and so if we want to find what R is, which is what the correlation is, we square root that. That's why we get 0.976. We should be able to interpret the R squared value. 95.3% of the variability in the yield, or the board feet, is explained by the model. Same interpretation we talked about before. Number 3, looking at the residual plot, I see structure there. There's curvature. There's a pattern to the errors. So a residual plot that shows structure indicates that errors are predictable with a linear model, which means that there's a more appropriate model out there, which would be a nonlinear model. All right, so that's number 3. And I'm going fast, but remember you can pause this at any time. Number 4 says, okay, so the model was not appropriate, so we transform the data, and we see that what we did was we take the natural log of y and we took the natural log of x. Okay, and we ran a regression of those things. And when we ran the regression, we got this residual plot. We see that it's pretty unstructured. We also see that r squared has increased. So this is an appropriate model. It's better than the linear model, and the residuals are unstructured. It's log versus log, so it is a power model. Remember, log versus log is power. Log versus x is exponential. Now you might say, what about y versus log of x? Well, we haven't talked about that, but it's neither power nor exponential. It's actually called logarithmic. Okay? All right, use the model to predict. So we're simply going to plug in 30 into this regression equation, making sure that we're looking at the logs of things, and then we get that the log, the natural log of the board feet of the yield is this. This isn't the answer, so then we have to transform that back by taking e to 4.75, and we get about 116. And if you look at the original data, 116 for 30, 116 is in here somewhere. It kind of makes sense. All right, so how confident are we? We're pretty confident, especially since this is an interpolation. This is within the x values of data that we have. All right, number 7. Use the model to predict for 55. So we do the exact same thing. We plug in 55 here. We get 776, but we're much less confident in this because it's an extrapolation. Okay. All right, so number 8. We're given summary data about latitude and about temperature. We're given that the correlation is negative. A says find r squared and interpret in context. So obviously we square r and we do our same interpretation that we've always been doing. Okay, the correlation is negative, and in context that means that cities that have higher latitudes will have lower predicted temperatures. And if we're in the northern hemisphere, which we are because there's a U.S. cities, the further north we are, the higher latitude we'll have, and that means generally lower temperatures. C has us write the equation of the regression line. We're given the summary data. We're not given the data. We're not given the Minitab output. If I look at this equation right here, this is how we will find the slope here. So I'm just going to plug in the values that I'm given. 0.848 is the correlation. The standard deviation of y, well, we're predicting the January temperature, so that y is the January temperature, so that's where the 13.49 comes from, and x is 5.542, the standard deviation. So we plug in and we get negative 2.11. We know that the regression line will go through the mean of x and the mean of y. So I'm going to plug that point into y equals a plus bx. I'm going to plug in the y, 26.44 in for a, and I'm going to plug in 39.02 for x, and I'm going to solve for the y-intercept, and I get this. So here's my regression equation. Then we're asked to interpret what the slope means in context, something we should definitely be able to do. Okay, really important thing. And this means that if the latitude goes up by 1, we predict the temperature will go down by 2.11 degrees. So for each degree higher in latitude, we predict a 2.11 degree decrease in the January temperature. All right. Letter E says, suppose that it is appropriate to use a normal model for both distributions of latitudes and temperatures of the 55 cities. If a certain city is in the 90th percentile for latitude, what percentile would you expect that city's temperature to be in? Okay, so first of all, let's think about what we need to do. First of all, if this is a picture of the latitude distribution. Okay? The 90th percentile would represent when the area below this curve is 0.9. Okay, so the first thing we need to do is to find the z-score for that value. Okay, and we know that we can use the inverse norm function to do that, and we get 1.28. Now, we could actually then find the actual value of that percentile by plugging in, x minus, we have to look at the mean, 26.44. Now, is this latitude? Yeah. No. So, 39.02 over that standard deviation, which is 5.42. And we could set that equal to 1.28 and solve for x. However, we don't need to do that. We discovered in class when we were looking at those suns and heights that if I standardize the data, the slope of the regression line is actually r. Okay, so if I'm looking at the predicted z-score for y, that's just r times the predicted z-score for x. Now, why is there no y-intercept? Because when we standardize the data, the means become 0. The standard deviations become 1. So this equation here, right here, is 1 over 1 for the slope, and that's why it's r, and the y-intercept is 0 because it goes through this point. Okay, so we can use this relationship right here to find the predicted z-score of the y. Okay, and so if we do that, we plug in and we get that the predicted z-score of the y is negative 1.09. We multiply r by that value. Okay, so what does that mean? If I were to draw a picture of now, this is the temperature distribution, I see that here's my z-score. I want to know the percentile. So I want to find the area. So we're kind of going the other direction here. And in order to do that, we use normal CDF. We're finding the area under this curve between negative infinity and negative 1.09. If you use that in the calculator, you get negative 0.137. And that is about the 14th percentile. Okay?